Good morning everybody, my name is Marco Walter Bassignana and today we make a lesson about object blocks. So first of all let's open a project which is a base project I always use to start for my developments. Here I have this base project with 3 axes emulated, one encoder which is not used, and the virtual master which is just using a virtual axis based on registers. There is no feed bus. Here the power set is controlling these 3 power set, these 3 axes. We use an RP2 and we work at 250 Hz of a fixed frequency. Inside the programs we have a task and a rule. They are similar to the standard task and standard rule that I always write during my previous lessons. And then, in Flash, we have these files. You may see many ones in the alarms, so yeah, we have so many useless ones. We can just cancel. Today we are playing OB. We are not here to show how many languages our system can handle. Okay, one less. Yeah, very well. Confirm. Now, okay, that's much better. And now here we have this debug, which is also useless part. Lost reg will be good, and so we can start. All right. Now, let's talk about object blocks. Here in the documentation of RDE, you can see the documentation of all the existing object blocks. If, for example, I open the book of the element location, here I can see a general description of this kind of class. I can see some version history, and here I can know something about the methods, the properties, and what I can do with this kind of tool. And then here we have the same documentation for all of our object blocks. Robox already allows you to use the PLC open part. Here you can see them, all the PLC open list. Together with them we have many other interesting object blocks. We have the handling of step trains. We have some models, for example we have the rod crank model. We have a recipe handler, and we have many other functions used to move axes in a very smart way. But sometimes you do not want to include an object block which is already developed, but you want to create your own. The advantages of creating your own object block are so many ones. For example, an object block is a secret, so everything you will do inside the object block before its compilation will be your own secret. After you compile the object block, you can just take the OBB, so the compiled file, and share it with anyone you want. No person will be able to decrypt and find the code you wrote, so your knowledge and your secrets will remain only yours. And the customer will only be allowed to use your object block inside the workspace you want him to use. So, for this reason, you should always keep a workspace separated, such as here, you may just make the object block and then compile it and use it in another workspace where it is only used but not programmed. So, all the part related to its code will be your own secret. Now, for this sample, we will just create and use the OB in the same project. So this could be the project you may use to create your OB. Then later you will just share it with your customers. Now the object block is written in C++. As you know, the R3 programming of Robox are written in R3, in fact, which is our language, but is derived from C, and the OB is a C++ standard. So, if you want to make it, you can just use your code that you may have developed on your own PC. You have just, for example, some codes related to some algorithm, to some motion, to some mathematics. You may just copy this and paste inside an object block, compile, and it will be suitable to be used. Now today we make an OB doing some functions just for test. For example, I now want to begin, so right click, new, object block. Here I give it a name. Let's call it RC, for example, and yeah, let's just call it test OB. Description, this is Marco's lesson. Okay, and then we need to define the folder in which we should put the OB. The folder normally is the OB folder that it's not available right now. So, first of all, automatic generation of, I can already start. I already clicked the automatic generation of implementation source files and overwrite any existing file. I press OK, and here I can already see that I have 3 files, an OBS, a .h, and .c++. But first of all, let's go to the Flash folder, right-click, New, Folder. And here we go at the end and we find the OB folder. This is a system folder in which we can put the object blocks. Now let's go again to the program. Right-click on the OB, and in Properties we can change the folder and choose the OB. Select and OK. Now, if I go again in the Flash, I can see that inside the OB there will be this rc test-ob.obb, which will be a binary file. As we said before, it's something undecryptable, and so it will keep all of your secrets like a black hole. Here the file you see is scratched. That's because we didn't compile it yet. So the system wants this file. We know that's a system file because it has this blue picture in the top left corner. As you can see, other files like the lost reg and debug are user files, and so they do not have that kind of icon. So we know that's a system requested file, but it's not available yet. Now let's go to program. Let's open and see what happens inside the object block. We open an OBS. Oh yeah. Now let's do like this. And then let's open the .h and .c++. Very well. In the .obs we may have a title, we may have a version, and here we can write some info. This is OB lesson. And then I say BR, which means break line. So this will go to the next line, and I can write 22nd of November 2023. And then I can do something more, some info about what we are going to do. So OB this OB can move one axis, in like with sinusoidal, for example, and solve a second degree equation. All right. And again, I do BR to have a new line. Now that's just a comment, so it's not what we care so much about. Here we can define the structures we want, if we have any. Here we write properties, and so we can define the variables that can be the input and outputs of our OB. Class methods. Here we will write the functions we want to call. Then in the .h, here we have the public part. In the public, you can see we have the constructor and the destructor. Finally, in the CPP, we can have the prototypes of the constructor and the destructor. Any other thing we would like to do will be added by us. Now, let's begin. with OBS. So inside the OBS, I want to add some properties. For example, our OB will make an axis to move according to a position, and this position will be a sinusoidal. So first of all, we need to provide some data. As we all know, sinusoidal parameters, we would like a sinusoidal to be function of time, and it has to be amplitude multiplied sine of 2 pi divided frequency and multiply the time. Okay, and finally we could have a phase plus, let's call it phi. That's the kind of equation that we want to represent. And so we will need real amplitude. This is amplitude. Then we have real frequency. This will be the frequency. The values we write here are the ones that could be seen from the external part of the OB, and every instance of the OB will be able to see it. When I talk about instance, it's because that's a class-oriented system. And so remember, while we will include the OB in this part in the configuration of our project, we will be allowed to instance many ones. So that's another very strong point of object blocks. You can make many more instances of the same thing. If you have to program something and you have to make it behave, to make all of this to happen more and more times, for example, one per each X, you will need that you may like to use an OB, because it will work such as a class, and so you can make more instances and handle all of them at the same time. So we have frequency, amplitude, and phi, which is the phase. Now let's go forward and let's generate something else. Read only real. So this is the IP, the ideal position. Position of sinusoidal. And then, for example, since we also want to add some other parts, we would like to use the second degree equation. So, for example, our OB is also using that kind of things. So, let's say we will provide the data in the function. So we will have other data here, read only real solution 1 and read only real solution 2 and read only integer number of solution. So that's number of real solutions of equation. So solution 1, solution 2. Very well. Inside the methods we will need two ones. One method will be update, and that's void. The other one will be an integer, and it will be solve equation of second degree. And here inside we want real A, real B, and real C. In this way we can solve an equation y equal a by x squared plus bx plus c. Let's say not, let's say that's the equation we want to solve. So a, b, and c are the parameters we have to send to the function. While the update, this will be the cyclic update called by rules to move the axis in a sinusoidal way. Okay, now that we have written these methods, we may copy them, come here, and here we paste. In the dot edge we must give them to the C++, and so we just need to convert. From R3 to C, you see, I have to do that kind of things. So, real will become double. And again, as you know, in C language, all the functions will have the semicolon. Now, let's copy them. Copy, and let's come here. So, let's copy, and here, let's make this kind of functions. Alright, first thing we have to do is the initialization of the OB. It is always very safe to take all of these values and keep them up to 0. So, amplitude is 0. In the same way, also frequency will be 0. Another clever thing is not to use capital letters to avoid the problems between case sensitive of C++ and not case sensitive of R3. We should never use the capital letters. So here we define in this way: amp, frequency, and phi. Amp, frequency, and phi. Then also the solution 1, the solution 2, and the number of solution that will be 0. Very well. Oh, finally also the IP. Good. Now, let's, for example, also use an enable. So here we will have an enable. This will be used to enable or disable the motion. And here again, let's put it lowercase, let's put it like here. Since it's Boolean, it's better to call it false. Well, so here inside we would like also some private. Protected. And here we will define some variables. For example, we would like double T0 and double TFB. Here again, we copy these two and we have to set them, so T0 equal to 0 and TFB equal to 0. Now, let's see. Let's start writing our code. If we are not enabled, we will just do nothing. If not enabled, we will just say that IP, we will not modify the IP, that's better. And we will say that T0 is equal to TFB. TFB is something we have to read. TFB is a parameter that the Robox environment allows us to read from the standard variables. Now, let's go and take a look at this. When we go in the programming language, here we see the object block library. Let's take the book. And here, let's see some of the functions we may read. TFB, read TFB. All right. This function reads the time elapsed from the controller switch on. Refer to the RDE manual for any detail on the predefined variable TFB. Excellent. So, here I can just say read part TFB. And that's standard time variable. Okay. So, if it's not enabled, we'll finish and return like this. Otherwise, we come here and we will say that IP is equal to amplitude multiplied the sign of 2.0 multiplied MPI divided the frequency. Oh well, frequency cannot be 0, of course. So frequency must be 1. So let's say if not enabled, or frequency is less than, let's say, an epsilon. Okay, let's say that we do not want something less than 0.1. In that case, we don't want the function to work. Okay, and so that's the TFB minus T0 plus phi. Very well. So that's everything we need to do. And finally we finish here. Now let's go here and let's solve the second degree equation. Here we know, first of all, we have to create some local variable. So they could be float, no, double. We have delta, and first of all, we may detect some easy solutions. So let's say if the absolute value of A is less than epsilon, we should define an epsilon. And so again here, no, we can make it better. We can just have a define. Okay, so in case A is too close to 0, we know that if B is close to, also B is close to 0, so there's no solution. That's easy. This means just C equal to 0, that either could be a possible solution if C is 0 or impossible. But for this sample, let's just make it this way. Otherwise, if B is different from 0, we know that solution 1 will be minus C divided B and return 1. Oh, sorry, the number of solution Never said what's the result. Oh yeah, the result may be, yeah, we can say that the result, we have the end solution. No, okay. I prefer solution. I prefer to make it a return. So function returns the number of real solutions. Very well. So and sol exists no more. So we make it, we take it out. All right, so no possibility, no solution. Otherwise, the solution is just one. And okay. So if everything is good, let's begin from delta, which is b squared minus 4.0 a and c. Here again. Let's say first, one possibility is if the fabs of delta is less than epsilon, so that's the double solution. Sol1 is minus b divided 2.0a, and the same for the other solution. So return 2. Otherwise, we may check if delta is less than 0, just return 0. There is no solution, no real solution. Very well. Finally, the only possibility is that delta is different from 0 and positive. So delta is sqrt of delta. And now we can say solution 1 is minus b minus delta divided 2.0a, and the solution 2 is the other one, minus b plus the square root of delta divided to a, and return 2. So let's see what happens. Now first of all, let's see and compile this OB. Compile. Alright, it tells me that we have a problem in the compiler, sorry. Configuration R3, no compiler. Custom, no automatic. Very well. Excellent. Oh, not yet. Sol2 was not declared in this no. Sol1 and Sol2. Now let's check what else is wrong. TFB was not declared in this task, this scope. All right. Oh yeah. I didn't give the prototype to my functions. Sorry. Since they belong to the object block, they must keep the same name. And here, all right, let's try again. I think that's good. Good. Now the OB is compiled, and so here we can include it inside our task, inside our system. Right-click, New OB class. First of all, the system will try to show us all the library of the predefined object blocks. After this, we can see the project object blocks, and here now we can take it. Look at here. Here we have all the kind of nodes we have written before in the OBS. Remember, the OBS is the interpreter, so is the initial page of the OB that could be used to communicate between the R3 world and the inner part of the OB, the black hole that we will never see. Only thanks to these properties and to these methods we can deal with what's inside. After the OB is compiled, that kind of code is secret, and so your customer will not be able to know what you did. So we just see the nodes, and now we confirm. Confirm. Alright. Now in this OB we may make an instance, and let's call it let's make this is test object block, and here it's test OB. But for example, let's make things funnier. Now, okay, let's begin with the easier way, then we will make it even more fun. Now let's go in the network, and here I'd like the address to go to port number 3. 255.255.255.0. Very well, confirm. And finally, here again we have a connection already done. Very well. Now we have this TOB. Now we can go and open the rule and the task. As you can see from the function list of the rule, here we have the init, prologue, epilogue, standard functions we already faced in previous videos, and then we have the rules: power off, fast stop, idle. This is the zero cycle rule. If you want to know more information about zero cycle, you can see some predefined examples, read the R3 manuals, or ask to Robox staff. Then here we have positioning, here we have manual, and finally here there is an automatic mode that's free for the user. If you want, you can cancel this and write what you need. The task 1 is also a standard task. Here inside we have the includes, we have the main loop where we have a prologue, alarm handling, mode change function for the FSM of operative selection, operative mode. Then according to the mode we will have a different function per each mode, and finally a common epilogue to write some output. Here is the init task. Here we set some variables. Here we set some other stuff, rules, then power allowed, and then we enable the power set. In the common prologue and common epilogue we will do something, refresh some register and some outputs in the epilogue. Finally, in the mode change, we see the structure that we already know, checking when the power is down, when we are in the fast stop, and otherwise checking the other modes and changing among them. After the operative modes, here we can see all the functions related to each one, where we can erase and reset some flags, and then we can of course assign the RC1 to the relative value. And here at the end we refresh some parameters about the maximum strokes and minimum strokes of all the axes. And finally in the alarm function we just see that when the reset alarm register is pressed, I will reset the alarms and reset the channel faults on the power set. That's a standard task, so that's very useful to start from this to begin our own code. So now let's go in the rule. And here in the task, for example, let's say that IV1, and IV2, or better, let's take IV2 and IV3, and they will just stay to 0. This to do, it's written all together just to become a keyword, is now cancelled, and now here I can say IP x01, and that's equal to testob.ip. In this way, we will call the instance we have already made of the OB and call the variable of the IP defined here in the OBS. In this way, the OB will control this X. But that's not enough. Since the update of these kind of things is done in the update part here, in the update function, we need to call the update function synchronously in the rule. And since here in the automatic rule we want the object to be updated, it could be good, for example, to update it in the prologue or in the epilogue. For example, if the OB needs something like reading some variables, for example, it depends from some input, it could happen at the end of everything in the common epilogue. Of course, the position given in the rule auto will be in delay of one sample interval, but the OB will have all the correct variables already calculated by the rest of the rule. Otherwise, like in this case, we have nothing to do and the OB is just working on its own and its own mathematics, we may just update it here in the common prologue. So the current rule auto will already have an updated value of the IP to be assigned to the IP of the axe. So tob.update. And here we call the update function. Now, in the task 1, we may come in the common epilogue, for example, and here we can ask if rise solve equation. We can ask the TOB to solve the equation of second degree given by some parameters. And for example, these parameters may be given by some registers that we can modify runtime. Let's come here and open the litreg. We move the litreg here. And for example, let's go to find some not used registers. I'd like, for example, here some not volatile real registers. And let's choose 3 lines and write lit RR, let's call A, B, and C, and VRR, and here are equation parameters. That's Controls Alt C, 5, 6, and 7, and that's A, and B, and C. Very well. Now, let's just copy this and use it as A, B, and C. In this way, we are feeding the function with the requested parameters. As you can see here, the parameters are A, B, and C. And so that's what we are providing. Now, let's save, and let's try to compile all. Let's generate all. Okay, I see no mistake. Right click, compile all. Oh, we have an error. Yeah, this register, this request was not declared yet. So that's a user request. Let's put it here. So that's R102.6. This is equation solve request. More than this, we can also get the number of solution. That, as we said, it's the outcome of this function. So we go to the begin and we write it here as a local variable in the task. Now, let's try again to compile. Okay, that's done. Now, since in my RP2 there is an old project, I rebuild. And as I said before, during the rebuild, we don't want the f-at, otherwise we would erase what's inside, and so we would lose the RDE operating system. If you remember, the difference between rebuild and make is that the make will just update the files requested by the current configuration, which are newer than the files stored in the RP2, while instead rebuild, that's what I'm asking now, can be used when you want to load the project on your controller for the first time. So, I don't know what's inside the controller, maybe some old project, maybe some other stuff. So, the rebuild will erase the selected folders before loading inside my files. In this way, I have the opportunity, but also the danger to lose something important. So I must use it only if I know what I'm doing. For this reason, never cancel the f-at, because otherwise we would write only the RHW over it and forget about the operating system, which is not inside this project. Now I click on all of these things and confirm. In case you are not allowed to reboot your controller, maybe it's because it's on power. If you need to put it to stop the power, you can press an emergency to have an alarm less than 2000, or if you prefer, you can just go on the shell and write power allowed equal to false. Normally in a shell you could keep it as a standard command. Right click on the shell, and here you can see it power allowed equal to 0. To have it, you must go to set quick commands, come here and write it in a comfortable place. This shell is the one I have made with the commands I like to have with the fast key. So, just pressing that kind of key, I'm allowed to play all of these interesting commands. That's very useful to debug in a faster and more convenient way. Now the RP2 has a reboot, and I can see the normal alarms. I can see, maybe we can also see from here, ALS. Yeah, user register loss, alarm history loss, unable to read persistent global variables. That's because I have put a new project and the RP2 is understanding this. If I make a mistake, I can switch it off and check what's inside my SD card. If I think that inside there should be the same project as before, but I see that kind of alarm, I still have the opportunity not to lose the values of all the NVRR and all the retentive memory of my controller, but I need to find what's wrong in my SD card and put it as requested before. If now I press 3 times the advance, I will accept these alarms and I will reset them. In this way, the controller will understand I really want the new project to be taken into account, so everything will be erased to start from 0. All the not volatile registers will be reset. And then, the lost reg file, if present, will be executed at once. In this way, the values stored inside the lost reg will be loaded as the first values of our not volatile registers. From now on, at every boot the system will not do this kind of thing, because it will see that the system requested by the SD configuration file is the same as the one saved inside it. So, now I press ALS again and I see that the only alarm I have is the emulation axis. Now here, since this project is already developed enough, I already put some graphic panels. If you wanted to know how to play the graphic panels, you may see the movies, the videos on YouTube about the RDE and R3 programming. Here I have a 3D panel playing the axis. Other things that I can see is the oscilloscope. In the oscilloscope we can see the position and speed and other important information of some axes. Now let's take our panels and see what they can show us. Alright. Now, for example, here in the graphic panel we can see the alarms. Now we only have the emulation active. So I will just look for the alarm reset. Actually it's not here. So I will copy and paste this and use it as alarm reset. I can go here in the task, go in the handler alarms, copy this and use it here, monostable. Very well. Now let's play. Let's reset the alarms. I give the feedback and I give power. Good. Now maybe in the oscilloscope, okay, I have a more interesting oscilloscope, a generic oscilloscope that will show us some more generic part like all the IP and IV and the operating mode of our system. So that's more interesting. Let's switch it on. As I said, now we are in idle. If I go manual, I can move the axis 1. You can see on the 3D panel here on the left, the yellow cube is moving and representing the axis 1 moving along the x-axis, the red one, the red line. Axis 2, you can see it's the gray cylinder, and it's going positive and negative. Finally, we have axis 3, that's the blue square, the blue cube, positive and negative again. Very well. Now we can, for example, press the start button. I will pause it and okay, and now now we have a problem. So, first problem. We can check our OB, dv TOB. And TOB is telling us that frequency is 1, amplitude is 0, and phase is 0. It's not enabled. The IP is 0, of course, and we have no solution to our equation. So, let's begin doing amplitude equal to 5. Oh, sorry, it's not just amplitude, but it's TOB dot amplitude equal to 5. If now I say dv again to the OB and I just ask dv the TOB amplitude, it will be 5. The frequency is 1, the phi, okay, it's not important, it may remain in 0. And now let's play and say TOB.enable equal to 1. Sorry, I forgot letter E. Very well, and now here we see that the oscilloscope is showing us the IV of axis 1 moving in a sinusoidal way. Now we can try to increase the TOB.amp. Of course it will go up as a step, but we do not care too much. Okay. A more clever OB would like to change things only in 0, but okay, that's just a sample and we like it. So 30, no, 50, yeah. Very well, and we can also see on our 3D panel the cube that's moving. If I move it like this, we can see it maybe even better. Here we can see the speed of the axis 1, while 2 and 3 are not playing. Now, let's ask the other part. Here we say that we would like, in the common epilogue, to have the solver of the equation. But to play this, first we would like to play a little more with our graphics panel and to add some more parts. So let's go to 400, and now let's put some variables and a button. The button will be monostable, and here it will be the request to solve the system, the request to solve the equation. Now here we will put A, B and C. So we will play top center RRA and copy and paste here as variable. Since that's a real value, we would like just to keep 2 of precision, maybe even 3. It could be more interesting. Copy, paste. Here we will have B. And finally, here we can put C. Now let's move them up here. And here below we want the number of solutions, so ends all. I do not remember, but I'm quite sure this may easily understand that I'm talking about the variable in task 1. Since the variable is only 1 and it's not duplicated in the other points, in other tasks or rule, this should be easy for the system to get it. Now sol2. For solution 1 and solution 2, of course, I have to say TOB dot solution 1 and solution 2. Now, let's play again. Alright, now first of all, we would like to write some values. And writing some values means RRA, for example, let's say RRA is 1, RRB is 5, equal to 5, RRC is 6. And now let's solve the equation. And we see that the solutions are 2. We have 2 solutions, which are -3 and -2. Anyway, we never had any stop in the operation. That's because the rule and the task execute in different times due to the scheduler. So, while the rule is calling every time the motion, the task, just when it has time, it will come here, see the rise of the request, and just ask the OB to make this quick mathematics calculation. Now let's make something more interesting. If RRC is becoming a giant value, I will go to a complex solution, and so I will find 0 real solutions. Otherwise, if A is 0, RRB is 3, and RRC is 21, I would like to see only one solution equal to -7. Yeah, only one solution, only -7. Very good. So, this means that what we see right now is a good working OB, both working for some function just called at event in the task, just to make some calculation, or if you want you can use a synchronous update in the rules, and in this way you can use it to move your X. One possibility, let's say, is that you may have more instances of this OB. Now, let's make a test. Let's play with also number 2 and number 3, and let's call them TOB1, 2, and 3. We want all the three axes to use the same behavior. I should not copy and paste the code. That is what I should do with any kind of function. Thanks to an object block, I can just use more instances. Then I just need to remember also here to keep the update number 2 and number 3. And here in the task, again, I can also use a number 0 just to be used in the task for this function. Let's say, normally it is strongly suggested to keep your OB just to do some kind of operation and to be called just by one task or by the rule. It's not suggested to use it both in the task or in the rule, unless the things doing in one of the tasks is very little. But now that's just a tiny example and that's not bad. But if you have some motion OBs, it is better only to use them inside the rules to avoid any other problems. Now let's play like this. We want 3 OB and we want to play all the 3 axes. Let's go to automatic rule and here let's wait. Now we save everything, we come here. I take out the feedback, so you see the fast stop. The fast stop ramp, it's here. You can see from here getting down. Almost the shape is similar, looks similar to the sinusoidal, but I can tell you that's not. We can make some more debug and see some more of the power of the oscilloscope. Here, if you want, you can do some calculation, like multiplication or derivatives and integrals. Since we wanted to say that this is a ramp and not a piece of the sinusoidal, we wanted to see the derivative, so the acceleration. Here I can go and check dA on dt of the IV1, which is track number 2. Here we know that this may be maybe 100, maybe even more. I don't want it green, let's choose a color that's not being used yet, for example violet, and let's see it. Oh, my scale is too little, so 1000. Alright, now you can see here that the derivative is always a cosine, because it's the derivative of the sine. And then, finally, when we begin the fast stop procedure, you can see the operative mode in the red part, the red line here. When we go from automatic to fast stop, the derivative, so the acceleration of the axis 1, is becoming constant because it's just an acceleration to ramp down the speed towards 0. Alright. Now that we have also seen this, I can right click and disable, so it won't be a problem anymore. Now let's just do a make. Oh no, sorry, I cannot. First, I must come here and call it TOB0. Then right click and create another instance. Let's make it even better. TOB, let's call it, let's make it different. This TOB0 will be just the one used by the task, okay? So it will be used here. While the other ones, since they are so many and we do not want to make all the instances, let's make an array. So that's again TOB. And this is an array size of 3. And here is motion OB. Very well. Now we generate all. We go again in the rule because now I must use them as an array. So alt, we do like this, and then let's do 0, 1, and 2. Let's copy and paste in the rule prologue where there is the update function. So in this way we can declare an array of these OBs, and so it's quite easy to use them when you have a big list of them. That's very useful right now, since we have more axes playing this OB. We can use all of them just with an array. Now I have modified also the axis 1. Now we go to the task 1. Alright, they should be good. Let's try to do a make and let's see what happens. I also would like to keep selected the OB folder in case we make some modification to the OB, it will be updated too. Now, set the loading mode will make the load faster, but the RP2 will no more execute the current program. So at the end, you should automatically reboot. If you just want to load files over your controller, but you do not want to reboot and you want it to work, so you have not to select this. In this way, you can just load the files, and then, when you will have time and you will reboot, the new ones will be taken into account. Now, since we are okay to reboot, we'll play like this. Okay, now it's loading tasks and rules and so on. Here we can do something very beautiful. We can take another beautiful square just to make it even more beautiful. Here this can go more inside. And here we may also change the color. I don't know, maybe this ugly blue. That's nice. Save the workspace. Save, because if the computer shuts down, I do not want to lose all of my job. Okay, now let's see. The RP2 is already switched on. Oh, sorry. Now the system is telling me too few indexes for TOB sol. Yeah, that's right. Okay, this is the TOB 0 because it's the one we will use in the task just for the mathematics. In this way it will be separated from the ones in the rule playing for motion. Okay, now we are connected. Here we connect also this. Let's reset the alarm, give the feedback and give power. And the operating mode we see is going from power off to idle. Now let's play RRA. We play again equal to 1. RRB equal, let's play again to 5, RRC equal to 6. Let's say RRB in -5, so we change the sign of solutions. And now, yeah, the solutions are now +2 and +3, while before they were -2 and -3. But now, let's talk about the other OB. TOB0 dot amplitude. It can be 5, while axis 2 will have a bigger frequency that could be 10. And number 2, let's say 20, even more. And let's also modify the frequency. So number 1 dot frequency could be 2 Hz, and it could be the same also for number 0, and the number 3 remains default at 1 Hz. What I also wanted to see was the phase, so let's modify the phi, and let's put it 1.57, so half pi. Let's see what happens. Now, start. Oh, now I see, yeah, I should enable, so TOB, okay, I want them to start at the same time, so I want TOB 0 to enable equal to 1, but I would like them all, so I will say, I will do like this. This way I can give more commands at the same time. Alright. Now let's start. Okay, Now they are very, very tiny. Let's see. Yeah, this can be smaller. This can be smaller. And number 3, which is bigger. Alright, now we see. They have different amplitudes. The 1 and 2 share the same frequency, while 3 is different. And 1 and 2 also have 90 degrees of phase. We can see that almost when the first is going to the maximum and the second is going to maximum, they are almost close to the 0, one to the other. So yeah, that's not precisely, but that's almost what we wanted to see. Alright, now this is everything we need to know about object blocks. You can now try to see some of the predefined examples of RDE. Here in the workspace you can see the special list of examples. Here there is something about the element location, the path jerk, the use of OB implementation, and some very interesting projects where R3 programming is playing together with object block, the same as we have done right now, playing like synchronous machines, playing with Flopax, cam demo, rod crank, and so on. I suggest you to see the predefined examples. In this way you will get more familiar with object block.